Okay, thanks, Shweta. Thanks for the introduction and thanks for the opportunity to speak here. So I'm going to talk about this joint work with Michael Levin that we're writing up now. We've been working on this project some time, at least a year or so, and it's about the stability of gapped Hamiltonians to long-range interactions. And this project sort of grew out of a different project we were working on where we encountered a problem that could be put in terms of a nice short-range Hamiltonian perturbed by a strange long-range interaction. And we didn't really have any good arguments about the stability of this system, no good physical arguments, and none of the mathematical tools that can be used for short-range perturbations were applicable. So we started thinking about this problem just in general thinking about stability of gapped phases with long-range interactions. So that's what I'll tell you about today. Feel free to interrupt with questions also. So here's an outline of the talk. So I'm going to discuss the stability problem in general, then contrast the case of short-range versus long-range interactions. And along the way, I'll review some of the results that are known when the perturbations are short-ranged. Then I'll discuss some problems that come in when you try to think about stability to long-range interactions, and also discuss how the known methods that apply for short-range perturbations fail for long-range interactions. After that, I'll present a family of models that's representative of this type of problem. So it'll be a nice short-range Hamiltonian perturbed by short and long-range interactions. I'll state our result about that model and give some examples of familiar Hamiltonians where this result applies. Then the most technical part of the talk, I'll sketch the method that we use to obtain this result. And that'll be just a sketch, and that'll be towards the end. So it's not crucial to spend too much time on that. And then I'll just conclude with some open questions. So to start, just very broadly, we all know a lot of interesting, exactly solvable models for gapped phases, and these models have a lot of interesting and possibly useful properties. We can never realize any of these models exactly in the lab. We'll always get possibly a nice model that we want with some perturbations added on. And these perturbations, we don't exactly know what they are. They could be short range or long range. In fact, in the first talk of this winter session, we heard about systems with interesting long-range interactions. And so you can ask, are the interesting properties of these models stable to generic perturbations? And by now, there are actually very powerful and general results for when the perturbation is short-ranged, but almost nothing is known for the case of long-range perturbations. And the sort of key example of a long-range perturbation is a power law interaction. So that's the type of perturbation we'll be discussing today. So the stability problem, it can be phrased like this. So we have some Hamiltonian H that's the sum of two parts, H naught plus lambda V, where this H naught is a nice model Hamiltonian that we know everything about. It's usually exactly solvable. It may have exact ground state degeneracy, a finite energy gap above the ground state sector, interesting excitations like anions, etc. And then we turn on some perturbation V with a dimensionless coefficient lambda. And this V is some generic perturbation term. We don't want to assume that much about it. And the question is, do all the nice properties of our H naught survive when you turn on this lambda? And do they survive for a lambda that's independent of the system size? So if this lambda went as 1 divided by the volume of the system, then by convergence of ordinary perturbation theory, the nice properties will survive. But this V is an extensive perturbation, and so you want to know, do all these nice properties survive when lambda is of order 1 and stays finite in the thermodynamic limit? So that's the key question here. And so one of the properties I want to focus on today is the splitting of degenerate ground states. So suppose that we have been able to solve part of the stability problem regarding the gap above the ground state sector. So we know that when we turn on V, the gap between the ground state sector and all the other excited states stays open. So we know there are still a group of low-lying states below the gap. Then you can ask, well, what's the residual splitting of all these states below the gap? They were previously exactly degenerate. Now they'll split a little bit. We know they're separated from the rest of the spectrum, but how big is their residual splitting? And in applications, we'd like it to be exponentially small in the system size. And the reason for that, well, one application is if you wanted to try to use these isolated states as a quantum memory, then if the splitting between these states was exponentially small, the time to rotate away from the state that you stored in this ground state subspace would then be exponentially large in the system size, which is a very desirable property. And if that splitting is not exponentially large in the system size, but maybe it goes as 1 over a power of the system size, that may not be good enough for some applications. It's not totally clear. So what I'll be interested in is whether you can actually establish still an exponentially small bound on the splitting of these states below the gap. So let me review some of the known results about stability to short-range perturbations. So the type of results that have been obtained, you can sort of broadly divide them into 2 categories, with some results sort of lying in the middle of these. And these were all for when this V is a short-range perturbation. And these 2 families of results differ by the properties of H0. So there's a good list of results where H0 is a classical Hamiltonian, like an Ising Hamiltonian, and then you turn on some short-range quantum perturbations. And the tools that people usually use in this case, one of the main tools is something called Polymer expansion, and we'll come back to that because that will be actually the tool that we are going to use as well. Another line of work considers the case where H0 is a quantum Hamiltonian, but it satisfies a topological order condition, so like the Toric code. And this is more modern work pioneered by Bravi, Hastings, and Michalakis. And this is sort of, the topological order condition here turns out to be essential for the stability. And it's an interesting result. The conditions that you have to assume are a little bit non-intuitive, but these results really cleared up exactly what kinds of assumptions you need on this H0 to guarantee stability. And these results depend strongly on the short-ranged properties of this perturbation because they use tools related to locality like Lieb-Robinson bounds. So there are all these interesting results for the case where the perturbation is short-ranged, but it's not totally clear how any of these results could be extended to the case of long-range perturbations. So let me give an example of the type of results that were obtained in those references. So consider the case where the H0 is just the Toric code on an L by L square lattice with periodic boundary conditions, and V is a generic short-range perturbation. So when the coefficient lambda is set to 0, we know the spectrum of H0, and there's a ground state sector that has 4 exactly degenerate ground states. Then there's a gap to the first excited state sector. Now this first excited sector, the number of states here is not order 1, it's of order of the system size because you can make an excitation in any plaquette or on any star. But we know the structure of the unperturbed spectrum. And then what was shown in these works is that when you turn on lambda, the spectrum kind of fans out from each of these bands of the unperturbed Hamiltonian. And the fan gets wider the further up the spectrum you go. And you can see, though, that there's a stability region where the fan coming out of the ground state sector is separated from the fan coming out of the first excited sector. And then, so that's the stability of the gap. The additional key result that they found here is that for the ground state fan specifically, the width decays faster than any power of L, the linear system size. And so it's not quite exponentially small in L, but it is faster than any power. of L. So this is basically an exponential splitting result. And this is the type of result we'd be interested in, but for long-range perturbations. I would definitely encourage people to look at these papers because there's some discussion of pretty non-intuitive properties of Hamiltonians where their stability result would fail and where you would think everything should be fine because the unperturbed Hamiltonian has a gap. So in these previous works, they used a definition of short range, a technical definition that allows the proofs to go through. And this definition, it does not allow for power law interactions. It allows for finite range interactions and interactions that have exponential decay. So the methods just don't apply. And very little is known, as I mentioned, about the effects of perturbations with power law interactions. So I'd like to take a few minutes and discuss some of the methods that are used to obtain those type of exponential bounds on the splitting when you have short range perturbations, and then discuss some of the problems with these methods when you consider long range interactions. So the two methods which I'll introduce, so one is a rigorous method that can be used to prove the exponential bound on the splitting, and that's called quasi-adiabatic continuation. The other one is an intuitive argument based on perturbation theory, and that gives a suggestion that the splitting should be exponentially small. And I'm going to illustrate these two methods in the example of the transverse field Ising model. So where H naught is this classical Ising term, and V is this transverse field perturbation with sigma x's acting on each side. So quasi-adiabatic continuation, I think it's maybe not widely known, so I made an introductory slide about this. And I would also encourage people to read a little bit about this method because you may never need to use it for any problem, but it's a very good way of developing intuition about gapped phases away from special exactly solvable models. So what this is suppose that we're considering this stability problem and we know that the gap between the ground state sector and the excited state stays open for all lambda less than some lambda naught. Then if all the terms in the Hamiltonian are short ranged, then for any lambda where the gap is still open, there's a unitary U of lambda that has two key properties. The first property is that it maps the ground state of the unperturbed Hamiltonian to the ground state of the perturbed Hamiltonian. If there's multiple low-lying states, then it does the same thing to the projector onto the sector of low-lying states. The other key property is that it maps local operators to local operators. It spreads them out a little bit in a controlled way so that the tail of this O quasi-local is under control and has rapid decay. And so, for example, if you look at this in the perturbed Toric code, you know in the Toric code we have these usual nice string operators, and what this U will do is it will just turn this into a thickened string operator, where this width of the thickened string is well defined because the decay away from here is nearly exponential. So using the existence of this U, it allows you to basically carry over all properties of the unperturbed Hamiltonian to the perturbed Hamiltonian. And
Matt, can I ask a...
Yeah.
Oh, sorry.
Mm-hmm.
Do you mind if I interrupt? So
go ahead.
These U lambdas, is there a sense in which there is a is it a continuum of U lambdas? Like, is U sort of continuous in lambda, or is the statement just there exists some for each lambda?
Oh, there's an explicit construction. Actually, it's constructed by a path order integral in lambda, like starting from lambda equals 0. But the construction it's a totally concrete construction for this operator. Yep.
Okay, thank you.
And the other thing I want to say about this is the price you pay for this locality property is that U does not map excited states of H naught to excited states of H. It will completely mess up the excited spectrum. So it has this nice property of mapping ground state to ground state and the locality property. But on excited states, it will do something basically completely out of control. So now how is this U used to prove a bound on the splitting? So let me illustrate this again in this transverse field Ising Hamiltonian. So H naught, its ground states are just these symmetrized and anti-symmetrized superpositions of the state where all the spins on the chain are pointing up and all the spins on the chain are pointing down. And then the ground states of H, we can obtain them by applying this U to these unperturbed ground states. And then what you do is you just look at the formula for the energy in this plus sector minus the energy in the minus sector. And you plug in writing psi plus minus in terms of U. And after a little algebra, you'll find that this is 2 times the real part of this matrix element, which is the amplitude to tunnel from the all up state to the all down state through the transformed Hamiltonian. And now this Hamiltonian has order L terms in it for a chain of length L. And then it's made up of local terms. So when U is applied to it, the terms that can actually flip all the spins will have an exponentially small weight because U keeps local terms local up to an exponential tail. So the result of this calculation is a bound like this where you have some extensive prefactor and then this exponential bound. And of course, that washes away the exponential prefactor, the extensive prefactor for large L. So that's how you can actually prove this exponential bound for short range models. And the quasi-adiabatic continuation method is very intuitive here because this is some type of instanton tunneling type of event you can think of. It really does look like tunneling from the all up to all down state, but not through the original Hamiltonian, but through this transformed Hamiltonian. So that was a rigorous argument, but there's another intuitive argument that's actually due to Kitaev. He presented this argument in the context of the Toric code, but it applies equally well to the transverse field Ising model, and it goes like this. So it says that the ground states of H naught have all the spins up or all the spins down, and if we consider perturbation theory in V, these states can't get mixed until order L because V contains terms that act on one site at a time. So we need to consider V to the Lth power before it can act on all the sites and flip all the spins. So from that, you get the idea that the first appearance of a splitting or of a difference in the perturbation theory expansions for E plus and minus doesn't appear until order L. So you get this type of estimate. And this argument, if you think about it, it actually doesn't use the interaction range. It only used the fact that V was a few body interaction. So if V, instead of terms acting on one site at a time, had terms acting on 2 sites at a time, we could apply the same argument and get an exponent of L over 2 here instead of L, and so on. And this should make you a little bit suspicious of this argument, and I'll come back to this later. But the problem is that this is an argument based on perturbation theory, but it's actually very hard to analyze ordinary Schrodinger perturbation theory for a many-body system. For example, trying to figure out what the radius of convergence might be is very difficult. So, okay, so now let's talk about the case of long-range perturbations. Actually, are there any questions up to now about what's been reviewed about the short-range case?
If I may, well, I can't understand why the argument is incomplete.
The perturbative argument?
Yeah. I thought this was the classic argument for whenever you have, say, degenerate ground states, symmetry breaking, and how perturbation would be lifted. What does it have to do with the radius of convergence? Is for lambda small enough, this is clearly true.
So the question is what it means lambda small enough. So the naive, so basically the problem is that there's no good way to figure out how big or lambda can get before this argument will fail. And there are examples of Hamiltonians where you add a term where lambda is of order 1 over system size and the system goes unstable. So in that case, the radius of convergence is very small. So that's really the problem. Is the question is how big can lambda get before this argument will fail? And it's really unknown in many problems. It's hard to get that information.
I see, but for infinitesimal lambda, this is valid.
Right. Yeah, so for infinitesimal lambda, this argument is fine, but what one would like to know is, can this argument apply for lambda of order 1?
Okay, so can I make ask a quick question related to that?
Sure.
Because what you said before actually implies that even infinitesimal lambda doesn't always work, right? Because you mentioned this scenario where the radius of convergence decreases with system size, if understood correctly. So then for any infinitesimal lambda, you can find a system size for which the radius of convergence is smaller, or did I misunderstand that comment?
What I meant is that there are examples where the radius of convergence must be of order 1 over the system size. So as the system size goes to infinity, the Hamiltonian is unstable, and this perturbative argument won't apply.
Right, but so isn't that a counterexample to the claim that infinitesimal lambda works?
Infinitesimal lambda can work in some examples, not others.
Okay, but so it's not so the argument doesn't.
Or I guess it at finite volume, there's lambda small enough it will work.
Oh,
but
sure. Right.
Size will be going as 1 over the volume or something like that.
Okay, thank you.
So that play out in practice. Okay.
Question. So this example you mentioned where it goes as 1 over L, that's an example with long-range interactions, right? I would guess.
Which example? The example of an instability?
Yeah.
Oh no. So if you look at the Bravi, Hastings, Michalakis papers, they look at a few non-intuitive examples where you can have a Hamiltonian with all short-range interactions and a short-range perturbation, but what happens is that the unperturbed Hamiltonian has a couple terms acting locally that sort of conspire to make the system very unstable when you turn on particular local perturbations. So that example occurs with everything short-ranged, where the unperturbed Hamiltonian has a gap, and you would think there would be stability. So there are some strange examples like that.
I see. But the previous, what you talked about in the previous slides for the topologically ordered case, there's no such, their things are well behaved and the perturbations are short-ranged.
So their example actually is for a topologically ordered system. Yeah, maybe I can just mention, if you go to these papers, I mentioned that they assume a topological order condition, and they assume actually 2 conditions, and one of them is the sort of standard one that we always think about, which is that a local operator acts as the identity in the ground state subspace. You know, you have to have very big operators that can not act as the identity there. But there's a second condition, which says something roughly like the kernel of local terms in the Hamiltonian should be consistent with the kernel of the whole Hamiltonian. And what it means is that you have a sort of local terms may have several ground states, but the global Hamiltonian maybe picks one of those out. And you can get weird counterexamples relating to this condition where the system is very unstable.
I see.
So there's some simple examples there, actually in the context of models that look like a variation of the Toric code.
It sounds like some pathology of the model, but maybe it's hard to eliminate that pathology with some simple conditions.
That could be. It's possible. Yeah.
Thanks.
But problem with it is that if you assume the standard condition that every local operator acts as the identity, then I think it should just follow, because every perturbation you have, which is local, is some local operator. And if all of them act as the identity, then all the correlation functions are trivial at long distances. For any finite number of insertions, the correlation functions are trivial. So I don't see how you can get this problem with the radius of convergence.
Well, so there's definitely interactions, at least on the examples, at least on the lattice, where you can get this instability where you're protected by the gap and everything is local. I'll also show another example later where this perturbative argument definitely fails for long-range interactions if the power of the power law decay gets too small. It's possible that it only happens in sort of pathological examples, but it's something that definitely can happen. Okay. So the question about long-range perturbations is that, is it even true that we can expect exponentially small splitting when we turn on a long-range perturbation? Conventional wisdom, partly based on that perturbative argument, seems to be yes, but the question is really why, because if you think about it, it's sort of more natural that if you have power law interactions, this would generally lead to a power law splitting. We have this perturbative argument, but again, we know of examples where it can go wrong. So this is the real question that we're going to look at. And let me just think about applying those previous arguments to this case and see what can happen. So in terms of rigorous methods, if we try this quasi-adiabatic continuation again, it turns out that now nothing is known about what U will do to a local operator. So before we had good control over how this U could spread this operator, but now we actually have no clue what it will do. In the case of exponentially decaying interactions, it's known that this U will produce a tail that decays slightly slower than exponentially, faster than any power, but slower than exponentially. So you would guess that if you have now power law interactions, the best you could hope for is a power law tail coming from the application of this U, but it's not even known. But in any case, that's not even close to the exponential decay you would need to prove that type of exponential splitting bound. And as I mentioned, the perturbative argument just seems too good to be true. And I'll actually show that it can fail for a power law with a small exponent. So on its own, it's not good enough, but I'll return to the perturbative argument later in the rigorous part of the talk and discuss how it can be improved. So this is the type of model that we'll study. So it's a typical model that has all the features that we're interested in. So, and it's the type of model that our method applies to. So in this case, H0 is a classical Hamiltonian with an energy gap. So I'll take it here to be the Ising chain of length L. And then the perturbation V consists of a short range term, which is just the transverse field Ising term. And then it has a long range term. In this case, it has sigma x interactions between distant sites. And the interaction is controlled by this function of the distance between the two sites, and will require for our result that this function has to satisfy a summability condition, which is that if I take this function and sum its absolute value over all possible separations, this needs to be bounded by a constant independent of the system size. And so, for example, in one dimension, that will allow power laws where the power is strictly greater than 1. And we'll see the reason for that soon, actually right now. So suppose you consider an interaction that violates that condition. So we'll take f of r as 1 over r and set the transverse field term to 0 because we're focusing on the long range interaction, and just do a variational analysis and look at a competing trial state where the spins are all in an eigenstate of sigma x with eigenvalue 1. I've denoted that by this arrow pointing to the right. Well, the usual ferromagnetic state with all spins up has 0 expectation in our Hamiltonian. And this trial state now, it has an extensive term, and then it has a super extensive term with an extra log factor. So when this coefficient epsilon here is negative, this new trial state is always better as L gets large enough. So you encounter an instability immediately when you take the thermodynamic limit. So this is a counterexample for this perturbative argument. It shows that you need to consider somehow the regime where perturbation theory is valid to apply that argument. The gap will not, the gap alone will not be enough to make that argument valid.
I have a question about this this summability condition. So does it, if we can go to the previous slide, you have things. So you have sum over R. Doesn't that imply that the F's must each be sort of very small when the system size gets large? Individual, just kind of regardless of like this range condition, but just small in magnitude in general because you're summing over a macroscopic index.
It means that this should be a convergence series. So, and this epsilon coefficient can become large. That controls the overall strength of this term. Yeah, you just need this series to converge as you take L to infinity.
Okay, thank you.
Yeah. Okay, so with these conditions in mind, let me state our result in this case. Or actually, let me just kind of pause for a second to just consider what are the interesting questions here. So this H, I didn't exactly mention it before when I was talking about the transverse field Ising model, but we all know H has a Z2 symmetry that's generated by the Ising symmetry operator where you just take the product of sigma x's on all sites. And so the Hilbert space breaks up into two sectors according to the eigenvalue plus or minus of this S. And H naught has a unique ground state in each sector. And it also has a finite energy gap. And for H naught, the ground states are exactly degenerate. And then so we'd like to know if similar results hold for H. So in this case, we'd like to see if there's a unique ground state and finite energy gap in each sector. And then after that, we'll try to get a bound on the residual splitting between the ground state energies in the two sectors. So I've drawn a cartoon of the spectrum here. So you see there's two sectors, H plus and H minus. In each sector, there's a ground state separated by a gap from the rest of the spectrum. And then I've drawn this red dashed line that indicates this residual splitting between E plus and E minus, which we'll try to bound. And so our stability result will cover all of these questions. So the result is that there are L independent constants, H naught and epsilon naught, such that if the coefficients H and epsilon are bounded in absolute value by these, then first there's a unique ground state and a finite energy gap in each sector. And then the residual splitting between the two sectors satisfies this exponential bound. And these coefficients C1 and C2 don't depend on L. They depend on the other parameters in the problem, but they don't depend on L. So this is an example, I think it's the only example we know of a proof of an exponential bound in a model with power law interactions. So let me just mention a few models that this applies to. So the first example, you could take the Kitaev P-wave wire model and add power law density-density interactions to it. And you could add them with a power alpha, any power that's greater than 1. So this model is related to our previous model by a Jordan-Wigner transformation. It's pretty well known for the Kitaev chain that for short-range perturbations, the splitting between the two nearly degenerate ground states with open boundary conditions is exponentially small. And then our result extends that to the case of these power law interactions. So they're still exponentially small, not power law small. They're guaranteed to be exponentially small for weak enough epsilon. Another example, which sort of started us on this path, is at the very first UQM seminar I presented on a model that we were looking at for a number-conserving topological superconductor, where it's very similar to that Kitaev wire, but now there's an extra degree of freedom that's a number and phase variable that represents Cooper pairs in a bulk superconductor that's attached to the wire. And the wire could exchange these Cooper pairs with the bulk, and there's an additional charging energy term that gives this model non-trivial dynamics. And we were able to analyze the stability of the gap in this model, but we weren't able to say anything about the splitting of the ground states below the gap at the time. But turns out this model, after a certain mapping, becomes a spin model, but now with an interesting all-to-all interaction where this f of r is equal to 1 over L. So it's again a long-range model that you can't apply the standard short-range methods to, but it falls under this family of models. And so now we can actually prove the exponential splitting in this model as well.
Can I ask a quick question about this slide?
Yeah.
Thanks. So for this model, fermion parity symmetry, is that a gapped symmetry? Are local fermionic operators exponentially decaying in this model? Or?
I don't actually know about the correlation functions. I would do this model. Well, actually, probably for this specific model, we can probably prove that the correlation function is close to what it is in the mean field model. But that was a specific result that we could prove for this particular model. We actually probably can't prove that, but in general, it would be very hard to obtain a result like that.
Right. Okay. But do you feel like it could be an alternative interpretation of the exponential splitting for this model, that it could be related to that? Like if the parity symmetry is gapped, that would probably be enough to show that the edge mode splitting is exponentially small. But
it's not completely clear because, for example, in the known bounds on correlation decay by Hastings and Coma, if you know you have a gap, if the interactions decay exponentially, then you're guaranteed that the correlation functions will also decay exponentially. But if you have power law decay of interactions, you're only guaranteed power law decay of the correlation functions. To establish an exponential decay would require extra work in the particular model or stronger bounds.
Right, but of course, if you have quantum numbers, such as fermion parity, it is well defined to ask whether a particular sector is gapped or not, right?
Certainly, and that those arguments can be applied looking at operators that map you between two sectors. In this case, if you consider the 2-point function of C's, then if you imagine inserting a complete set of states in the middle of the two of them, that set is in the opposite fermion parity sector, and it would be that gap between the sectors.
Exactly. Yeah.
The decay. But still, in that case, applying those arguments, they only guarantee power law decay.
Thank you.
Sure.
So a question about this interaction. So this doesn't obey your summability criterion, I guess, but you've tuned the coefficient to make it small enough. Is that the idea?
It does obey it because it just sums f of r over r from 1 to L. So you sum these and you get 1.
Yeah. Okay. Yeah. So you're kind of making it weaker the larger your system is, and
yeah.
So okay.
Yeah, that's right. Okay. So in the last part of the talk, I want to give a kind of a sketch of the methods that we use. So I guess I have about 4 minutes left. Maybe I can take a little bit more. So the basic idea of this method is to do a rigorous version of the perturbation theory argument. And what we end up doing is developing a controlled expansion that allows us to show that the ground state energy as a function of parameters is actually the real slice of an analytic function of those parameters. And this function exists in a complexified parameter space where h and epsilon can take on complex values. And this analytic continuation, the difference between the two sectors of this complexified ground state energy vanishes until order epsilon to the L over 2. And you can understand that because the long-range term flips 2 spins at a time. So that explains this L/2 power there. And then once you have these properties, then you can use standard tools from complex analysis to obtain an exponential bound on this splitting. And to prove these first 2 properties, we use a certain controlled expansion that's called a polymer expansion. It's a tool from rigorous statistical mechanics and constructive quantum field theory. What it is, it's a version of perturbation theory for the free energy of a system at finite temperature. And so we actually start by analyzing our model at finite temperature, and then later we take the ground state, and the expansion is under control enough that the 0 temperature limit is actually also controlled, turns out. So let me just give a brief idea of what's going on here. So polymer expansion applies to models where the partition function looks like a sum over geometric configurations x with some weight, w of x. And here x is a collection of elementary configurations that are called polymers. And these polymers have a notion of intersection. 2 of them can be intersecting or not. But in this sum, all of these x's have to be collections of non-intersecting polymers. And then the weights should factorize according as a product of weights for each individual polymer. A simple example where this structure arises is if you rewrite the 2 de-Ising partition function in terms of the domain walls, so these contours that would separate regions of up and down spins, then chi1 and chi2, et cetera, would be different domain walls, and then they would have some weight associated with the length of their boundary, and they naturally appear non-intersecting. So that's a typical example of this. In this case, what the polymer expansion gives you is an expansion for the logarithm of the partition function in terms of the same objects, now with some combinatorial factor here that I won't get into, but it's related to the combinatorics of just taking this logarithm. And then X is now a collection again of polymers, but now these polymers must all be connected to each other such that the intersections are such that you can get from one polymer to any other by, moving to one that you intersect with. If you think of a graph where the vertices of the graph are chi1, chi2, et cetera, and you draw edges between any 2 polymers that intersect, then that graph should be connected. And this combinatorial factor it's graph theoretic, and it's related to thinking about all those connected graphs. And this expansion is absolutely convergent under appropriate conditions. And the key thing for us is that when this expansion converges, it guarantees that the log is a holomorphic function of all the parameters in the problem. So that's how we'll get that holomorphic property. So in our model, the way this comes about is we consider the model at finite temperature in each sector of the Ising symmetry. And the way you get this type of expansion is you essentially set up a discretized path integral for this trace, and it's in imaginary time. And this X ends up being geometric configurations on the imaginary space-time, just by doing a coarse graining of the world lines of the domain walls on the spin chain. And so let me just give a couple little pictures of that. What one does to set this up is you introduce a lattice spacing in the imaginary time direction. It gives you this blocking in the time direction. And sigma x operators act at various points in imaginary time. I've indicated them by these crosses. And when they act, they make domain walls on bonds represented by these red lines. And then what you do is you just regroup all the contributions to the partition function according to a coarse-grained configuration, where if one of these domain walls goes all the way through a plaquette, in the coarse graining, we just color that plaquette in. And if a perturbation acts at some site J in a time slice, we take that box. And then finally, the key for us in this long-range model is if a perturbation acted between 2 distant sites, we connect those 2 sites, or those 2 boxes here, by a dashed line. And this is the key new ingredient in the long-range model, is these long-range interactions are represented by these dashed lines in this configuration. And so what one gets from doing this type of coarse graining is pictures that look like this, where all the microscopic contributions are regrouped into big contributions associated with pictures of these boxes and plaquettes and dashed lines. And in our model, the polymers end up being these connected pieces of boxes and plaquettes, but we also count things as connected if they're connected by a dashed line called weakly connected. And so you can see in this picture, there's actually only two polymers. There's one here that just consists of boxes and plaquettes, but then this other one takes up all of this space because it has dashed lines that connect distant pieces of it. And let me skip the bound on the weights to just speed this up. The key issue here is proving the convergence of this expansion. And it's known that to prove the convergence, it's sufficient to prove a bound like this, where one needs to sum over all polymers that include a particular box or plaquette. And the summand is the weight times this exponential factor. And the way to think about this is really like an energy entropy estimate in the style of Pyrrol's or Thales, where the sum over all configurations is the entropy part, but the weight is a Boltzmann factor coming from the energy. And if the weight decays fast enough, the energy wins. If the weight decays too slow, then the sum explodes. So in the case of short-range perturbations, these chi's are just sort of connected blobs of boxes and plaquettes. So what one needs to do for this sum is just sum over all these connected boxes and plaquettes that include this one box or plaquette V. And it's known that the number of these is exponential in the size of chi, but the weight can also, it has a piece that's exponentially small in the size. So if this coefficient mu here got large enough, then you can easily control the sum. With long-range interactions, it's not so simple now, because polymers you have to sum over are all of these collections of blobs that are connected by horizontal dashed lines. So you have to sum over all possible numbers of blobs such that one of the blobs contains this V, and then all the different ways of connecting them by dashed lines. And that sum is much trickier. It can be controlled provided that the interaction satisfies that summability condition. So that's what we needed to verify to prove convergence. And once you have that, you can put all these steps together to obtain our result. And so what we do is we consider the partition function for complex values of the parameters. That's okay, because it's still, the Hamiltonian is still a well-defined matrix. It's just not Hermitian anymore. The Polymer expansion gives controlled expansions for the complexified free energy, so the log of this complexified partition function. The zero temperature limit is also under control. We can take it to get the analytically continued ground state energies. And of course, these agree with the true ground state energy on the real slice of the parameter space. And then this gives us all the properties we need to give a rigorous version of this perturbative argument and really prove the exponential bound on the splitting. So let me just conclude with a couple of comments. So I presented everything in one dimension, but actually the results, same result holds for similar Hamiltonians in higher dimensions. The combinatorics works out in a similar way. Translation symmetry is also not needed for these results. So the key question here is to be able to handle models where this H0 is not a classical Hamiltonian, but it's really a quantum Hamiltonian like the Toric code. So a big open problem is thinking about the Toric code with generic long-range interactions or other models like that. Another question is how dangerous are the power laws when this power goes below the spatial dimension? So you may have noticed that that summability condition is exactly forbidding this. It includes the case of true Coulomb interactions. Stability in this case, we kind of still expect it, but it's interesting to think about how you would show it. One thing that's known in the mathematical physics literature is that if you want to prove things about Coulomb systems, then you really need to include also the neutralizing background terms. And so that may be necessary in this case as well. So I think those are interesting directions to look into. So that is the end of the talk. Happy to take any additional questions.
Yeah, thanks, Matt, for the great talk. Now we have time for questions. I think there are already 2 questions in the chat. Maybe Ruben and Bowen, you can unmute yourself.
Yeah, sorry, I didn't see any of these questions during the talk.
Oh, sorry, I don't want to take up more time, so I'll let Bowen speak.
Okay. Yeah, thanks, Matt, for the nice talk. I was wondering, so yeah, I was thinking about some examples to yeah, test my understanding. So for example, take the K-type chain, the 1D K-type wire. That's a simple model. In one of your slides, there was a 2-body interaction, which decays at a power law. And in that case, you said the power should be greater than 1. That's the case. Your method works. I was wondering, suppose I add a term with 3 couple GKL, 3 sides. What's the power that your method will work?
Oh, I see. So like Ni, Nj, Nk, something like that?
Yeah.
I suspect that it will still work for the same type of power. Probably, well, there will be some similar condition that will guarantee that that term is extensive. And I would guess that it will involve the same type of powers. I would guess that you would still get the same type of power. We haven't really thought about that, a 3-body interaction where the all 3 terms could be very far away. But if you considered an interaction like that, there will be some condition that would guarantee that that term would still be extensive, but not super extensive. And
I see.
I would guess that the condition would be similar. I'm not totally sure though.
Okay, good. Yeah, actually the coupling, what I was thinking was kind of the power between the, there's if you have 3 sides, there's a 3 distance. So maybe I was thinking about something decay with the power of the 3 distances. And yeah, the motivation is because I saw in literature there's some model with power law decay homogeneous. Some people were trying to argue whether you neglect some of the power law, it will make any difference. So I thought that will be interesting. Yeah.
I see. Okay. Yeah, no, I'm not familiar with those models, but I would guess that a good guide would be to think about the conditions that will make this term extensive.
Maybe just one comment. Just to clarify, maybe another way of saying what Matt's saying is, if you call that coefficient f of ijk, our best guess would be you want to take the sum of f of ijk for fixed I, summing over all possible, say j and k, and you want that to be less than some constant. So I think that's what we want. So you fix one of the, assume it's translation invariant. So fix I to be at 0 or something, and then sum over all possible values of j and k, and you'll have some coefficient f of j, k, and the sum of that has to be bounded by some constant, or that would be a guess. We haven't proven anything, but that would be our guess.
Okay, thanks a lot.
Any other question?
Do you have any guess for the Toric code with long-range interactions? Do you think with sufficiently large power, it would be still exponential, or you have reason to believe otherwise?
I would guess that you could obtain an exponential bound for large enough powers. The technical part is not clear how to do it, but I think based on the result that we've obtained, and it seems like you might be safe if the power is greater than the spatial dimension. You could probably obtain an exponential bound in that case. The particular method we used is not capable of handling that case for now, but I think the intuition you can get from this is it seems like you should be able to prove a bound like that. But for sure, there will be some condition on the power. That's definitely going to be true.
Right. Okay, thanks.
Sure. But that's a really interesting and open problem. So.
If there's no other question, can I squeeze in one last one on my part? So yeah, thanks a lot. That was actually very interesting. So still digesting it. I'm curious. So I don't know much about this, but I've heard of this other work. I guess there's several works where they study a Kitaev chain with long-range couplings, but it's just like a free fermion case. It's simpler to analyze, and I think they claim that it's algebraic if the hopping and pairing term don't have the same power law. So, but I haven't read it, so I don't know how convincing it is. So, is it just that your conditions don't apply to that case, or what do you, or what do you think might be going on there?
So it's I think I've seen some of those papers. So T and delta are long ranged. They both
right, exactly.
And
what they claim is if T and delta have the same power law, they claim to see exponential splitting, and if it's different power law, they claim it's algebraic for even no matter how large alpha is. But again, I haven't read the paper, so I don't actually.
It's hard to say. I mean, our result definitely applies in the case where you have control over the unperturbed Hamiltonian. And I guess in that case, I wouldn't exactly know how to split it into thinking about an unperturbed part and a perturbed part. It seems that there everything is entering on equal footing with power laws, at least in what I've seen of that type of model. I think it would be to say for me what there. I know that when you take a long-range model like that and you try to diagonalize by Fourier transformation, when it's sufficiently long-range, you won't get the expected nice gap spectrum, and certain other things go wrong.
Yeah, that's true, but that, yeah, that's for like alpha 1 or 2, but they're claiming I think for any alpha,
yeah, I'm not sure, but I'd be interested to look at it.
Okay, yeah, thank you very much.
Sure.
I think Taran had a question.
Hi, I have a question. Earlier, there was a comment that power law interaction may have some similarity with being coupled to a gapless mode. I was wondering if you can say a bit more about it, and also my question was more about when there are systems where there's some gapless degree of freedom coupled to maybe some let's say some gauge fields, for example, is fractionalized Fermi liquids or maybe HLR state or things like that. Is there some notion of still stability of the topological order as well as maybe splitting and so on? For example, you can still talk about splitting of modes which come from sort of topological sector. Can one say something about it based on these results?
So for the first part of your question, I think that I didn't totally see what was in the chat, but I think the comment, maybe Michael can clarify, but I think the comment was that if you have a model with long-range interactions, you can interpret it as arising from integrating out some gapless degrees of freedom that we're coupling to your system. And yeah, so that may be one way to interpret models like this, but I don't think I have any more to add to that interpretation. In terms of stability results, when the unperturbed system is gapless, that I think is very difficult. There are no formal results that I know of along those lines. What controls all of these methods is the gap of the unperturbed system. Yeah, I mean, it's a very difficult problem. It's very interesting, but very difficult.
Okay. Thank you. Yeah,
maybe in that case, just to add, maybe the best things that are known are the type of renormalization group results like Shankar-Polchinski, the type of results that indicate that certain perturbations to a Fermi surface are irrelevant, just like that. Yeah.
Yeah, I'm still a bit confused about answer to Ruben's question, because some of these older papers I was confused about when they talk about Guitaev chain, and they claim that with power law interactions which satisfy your condition, so that alpha is bigger than alpha beta are bigger than 1, alpha beta are the power laws of two kind of terms in the Hamiltonian. It's still, they still seem to claim that that the splitting becomes instead of exponentially small become power law small. At least that's what they. I haven't read those papers in detail. I'm just looking at their conclusion.
Well, maybe I can say a little more about that type of thing. So if the power law is on the T and delta terms as well, so something that's kind of known in the mathematical physics literature is that power law interactions are really tricky and lead to really non-intuitive behavior. So if you take, for example, just an Ising chain, but you make the Ising interaction power law, which is sort of like what's I imagine is being done there, where T and delta are becoming power law.
Right.
Then the dependence on the power is really tricky. So for alpha greater than 2, you have no long range order at finite temperature. But for alpha greater than 1, but less than or equal to 2, you do. But then when you go below or below again, you don't. And if you, instead of thinking about discrete symmetry breaking, you think about continuous symmetry, then the borderline cases of exactly 2 change.
Right. I saw that. Yeah. Right.
Can happen. So if you make all the terms power law, I would imagine that various different things can happen. Here, the only thing that's the power law is the small perturbation.
I understand. Okay. Yeah, that's the thing. Yeah, that's clarified. Thank you.
Sure.
Maybe another comment I could add in that regard is this power law is the most innocuous when you convert it into spins, the density-density interaction.
So Ashwin, we may have lost you there.
Can you hear me now?
Yeah.
So the Jordan-Wigner will give you a string operator if you have long-range hoppings or long-range delta, but not for the interaction. So I think it's not surprising if you're using the spin model really to make these arguments. I think it's not surprising that the power law in delta and T is much more dangerous than the power law in N, the NN term.
Yeah, I completely agree. Definitely makes sense.
Okay. Yeah. If there are no further questions, let's thank Matt again. And okay, we'll see everyone next week.
Hey, don't